Audible? Alright. Guys at the back, can you settle down? Is there anyone else we are waiting for? Okay, I think we should begin. Alright, hello everyone. So myself Suprovat Ghoshal. I'm a second year ME here. And this talk is going to be on randomized algorithms. I'm going to give a brief outline on what I'm going to talk about. So we are going to touch two problems. One is primality testing and the other is max-cut. And we are going to look at some naive approaches, see why those don't work. We are going to look for some randomized algorithms and see how good they are in those cases. We are also going to discuss the need for derandomization, and we are going to actually see one of the derandomized algorithms. Quickly moving on to primality testing. So let me introduce the problem like this. Say most of you know what primes are, right? Primes are a very interesting class of numbers. Many compare them to elements in among compounds. Like all the other numbers can be represented in terms of these primes here. Primes have fueled enough research in the last few centuries in maths and applied maths and other places, but they have also had a long-standing impact in the practical scenario. For example, all those encryption decryption algorithms that work in order to keep your data safe in the network, they are dependent on a problem which is known as prime factorization, and a critical step in that is to test whether a given number is prime or not. Now the questions could be like, is 2 prime? Anyone? Is 2 prime? Yes. How about this? Is 2 not 3 prime? No. So it's 29 times 7. But you see, it gets harder if you got bigger numbers. And if someone asks you this, then we got a problem. And suddenly you think like, okay, it's probably a good idea to have the computer work that out for you, right? And hence the need for an algorithm. So before we start, we're going to go over some preliminaries. I'm hoping that most of you are familiar with what natural numbers are. And I'm also hoping most of you are familiar with primes are. So primes are basically natural numbers which are just divisible by themselves and 1. Any natural number that's not a prime is a composite number. Along with that, I'm going to assume that you've got basic knowledge of probability. I'm sure you've encountered probability in some of the earlier talks, and whatever you encounter would be sufficient for the first half of the things. Now, to formally actually state the problem is to give, once a natural number is given as input, say x, you need to determine whether that number is actually prime or not. So here's a naive approach. So the largest possible factor for a given number x can be at most root x. So what we are going to do is, we are going to check for each number between 2 to root x, we are going to take them and we are going to try and divide x. So this notation here says that we are checking if I divides x. If we find such a number, then we know it's a composite number, otherwise it's a prime number. Seems fair enough. I'm sure you have encountered this kind of an algorithm sometime or the other. And the complexity for this is order of root n log n squared. This is because you've got root n order of iterations, and per iteration the complexity is dependent on the divisibility test you do, and that can be done in log n squared. But in most cases, as it so happens, polynomial in n is a good enough complexity, but it is not so in our case. Can anybody guess why? Yeah, exactly, right. So the issue is that to represent n, a number n, you need to, it's representable in log n bits, and the root n here in the complexity is something that is exponential in log n. So that in general is not a good, that says that we are not efficient enough. Now the lesson we want to learn from this is that we cannot be testing for all those numbers between 2 to root n. We can only test for some of those. So okay, lesson learned. Let's try something else. Instead of trying for all the numbers, let's just pick up some numbers at random between 2 to root n, and let's just find out if any of those numbers actually divide the given number or not. I'll say if we do this, if we run this algorithm, there is absolutely no chance of making a mistake on a prime number. And why is that? Absolutely. So that's the reason why there will be no mistakes made on primes. But in the case of composites, in the worst case, what might happen is the probability of making a mistake would be very close to 1. And those are like corner cases. For example, if you took a number which is the square of a very large prime, the prime number itself is the only factor there. No other number is going to divide it, and if the numbers you chose for this test do not include the prime number, then the test is bound to fail. So this again says us that this is not a good way to characterize prime numbers. We need a better way to characterize them. So this we need a test which gives you less number of true negatives. That is, we should be able to make less number of mistakes on composite numbers as such, and that is given to us by what is known as Fermat's little theorem, introduced by Fermat in the year around 1640. What it says is, if p is prime and you choose a number between 1 to p minus 1, let the number be a, then if you compute a power p minus 1 minus 1, it's going to be divisible by p. Let's break this down a bit. Let's dig deeper. Let's see what happens. What it says is, if p is a prime, then a power p minus 1 is going to be divisible by p if a happens to belong in this range 2 to p minus 1. Now in the earlier slide I had 1 and p also in the interval, but you can check that in that case for 1 and p almost the test would hold true for any integer. However, what it says is, if this was a prime, then p will most definitely divide a power p minus 1. But the question is, for composites, is it the case that if you chose a from the same range where p is a composite, would p always divide a power p minus 1, not divide a power p minus 1? So the answer is actually no. That is not the case. What actually happens is, even if it's a composite number, there might actually exist some numbers between 2 to p minus 1, which such that if you compute a power p minus 1, it would actually be divisible by p. We call such numbers as Fermat liars, because they fool us into thinking that these numbers are actually primes, whereas they are actually composites. Any number which is not a Fermat liar in this range 2 to p minus 1 can be called a Fermat witness. Now a point to be made here is, Fermat liars and witnesses are defined only in the case of composites, because we know this, that for primes the behavior is uniform. There are no liars in that case. The liars exist only in the case of composites. But here's a good news. The good news is that say there existed at least one Fermat witness in the range 2 to p minus 1, then the fact is that at least half of these numbers between 2 to p minus 1 would also turn out to be Fermat witnesses. What does this give us in hindsight? This says that if you actually chose a number between 2 to p minus 1 at random, then the probability of that number being a Fermat witness is greater than or equal to half. Or more importantly, the probability of that being a Fermat liar is going to be something strictly less than half. Right? So this gives an idea of how to actually go about the algorithm. So what we do is, we choose a number, given number x, we choose a number between 2 to, sorry, that would be x minus 1, and we do the divisibility test, which says it will divide x by a power x minus 1 minus 1. If the divisibility test is true, then we return prime. Otherwise, we return that we label the number as composite. Now let's analyze this algorithm. I'm claiming again, if x is prime, then the probability of making a mistake would be 0. Is this clear why? Can someone explain? Guys, I can't hear you. I'm a bit deaf. So, as she said, the idea is that this always holds true for primes. There are no formal liars in that case. So there is no way we can be making a mistake in that case. But in the case of composites, there might be a chance that we might be making a mistake. When does a mistake happen by the algorithm? The mistake happens when the input number is a composite and you label it as a, and the algorithm labels it as a prime. And when does that happen? That happens when you choose A such that A happens to be a formal liar for that particular number. But we know from our previous slides that the probability of that happening is something strictly less than half. So that gives us some breathing space. But still, half is a large enough error probability. We want something which is something very close to zero, say some epsilon. How do we go about that? Absolutely. So this is a basic trick that many places use. When you got a black box with an error of say less than half, you repeat it some t times. So in our case, we'll be going to repeat our black box algorithm some t times. And for each time we are going to select A independently at random. We'll be sampling without with replacement, and I'm going to claim again that if the number was a prime, there is absolutely no chance of making a mistake. Is this clear why? Same argument, nothing else. It's just the same algorithm working again and again. But for the composite, there is a chance that there is a mistake. And the mistake might happen when? The mistake might happen when, again, the input is a composite and the algorithm labels it as a prime. But for that to happen, all those numbers that we sampled, those need to be formal liars. Because if we got a formal witness among one of those, that would give us a definitive proof that the number that we got is a composite number. We'd stop then and there. So for all these t times that we sampled, we all got formal liars. But here's the interesting thing. We sampled it independently. So we can break this probability down into independent events, and we can express it as a product of probabilities. And we know that each of these probabilities is a quantity less than. Yep. So that gives us a probability of less than 1 by 2 power t. If you wanted something like epsilon here, then you need to set t as something like log of 1 by epsilon. That's just algebra. And the complexity of this is RT log n cube. Now the n dependent terms are all per iteration complexity, and t is basically gives you the number of iterations. Can anybody say what R here stands for? Take a wild guess. Who got that? Yep. So this is basically, it abstracts the subroutine that actually gives you a random number. So since the algorithm in reality wouldn't actually be tossing coins, it would just be running a subroutine which would return a random number, and to do that it would require some complexity, and that is abstracted in this R. So there are different ways to do it, but I'm not going to go into it, right? So this okay, but there is a flaw in this algorithm. When we said that the probability of obtaining a formal liar is strictly less than half, we did put one condition. The condition was absolutely. So there are numbers, composite numbers, for which say between the range 2 to p minus 1, there are absolutely no formal witnesses. So if you ran that algorithm on any number of times on that number, the algorithm will always fail on those numbers, and such numbers are known as Carmichael numbers. One famous example is 1729, which is also known as the Hardy-Ramanujan number, famous for different reasons, but there are infinitely many of those numbers, and so it seems that the algorithm would almost always fail on either on infinitely many of these cases. But why are we actually studying this algorithm, right? The follow-up to this algorithm is a bunch of state-of-the-art algorithms that we use today. That includes the Miller-Rabin test, which is a standard primality testing algorithm that we have. And then there is the famous AKS algorithm, which is the first algorithm which was deterministic and polytime in log n and was able to do primality testing accurately. So it led to such fundamental works, and this is a very simple idea which was used over and over again to get to these algorithms. This was a very fundamental piece of work, so as to speak. With that, I'm going to conclude, let's say, the first 1/3, and I'm going to ask if you've got questions here. Come on, guys. I know you're brilliant, but there should be some questions. Okay. All right. That is what exactly the Fermat theorem says. All right. Let's go back a bit then. Let's see. All right. A power x minus 1, right? And A is a number which is, say, as large as n. What is the complexity for computing this? What's the way to compute this? A power x minus 1. I mean, okay, let's say you need to compute 2 power n. How would you compute it? Can you explain that? Like, few words. Yeah. Okay. How about any arbitrary number? Let's say 5 power n. Say 5 power n. How are you going to compute that?
First, get binary representation of n.
Yeah.
Then start with a is equal to 5. If the last bit of that binary representation is 1, then first initialize answer to 1, then multiply the base if the last bit is 1, and in every iteration move left
Okay.
in the binary pattern and square the base. 5, 25, 25 to 25.
Yeah. So that seems to be the basic idea. The naive way to do this is to multiply a x minus 1 times, but the faster way to do it, first compute, say, a square from a, then we compute a power 4 from a square, and so on. So that basically helps us in getting this complexity. Otherwise, this would have turned up to be something like log n power 4 or 5, I'm not sure, but it won't be log n cube. All right. So this basically concludes the first problem. We're going to look at the second problem now. So this problem is a graph-based problem, and let me motivate it by this. So it's almost 3 days now, and you guys must have made some friends. I'm going to ask you, I'm going to play a hypothetical game with you, right? I'm going to ask you to divide yourselves into 2 partitions such that any pair of people, you need to maximize the number of people who know each other belonging to opposite sides. What I mean by this is, say I'm supposed to pay you some money. Say I'm going to pay you $100 for every pair of people who know each other, but they belong to different sides. Now this kind of a problem, if you are thinking mathematically, can be naturally expressed in terms of graphs. I'm going to ask you guys to pretend to be vertices, and then all your relationships can be modeled in terms of edges. And what we can do is, then the task would be to partition this set of vertices into 2 groups such that the number of edges crossing the partition is maximized, because for every edge that crosses the partition, I'm going to pay you $100. Now, keeping this hypothetical game aside, let's move on to the reality. I'm going to again look for some preliminaries here. So So we define what a graph is. Graph would be parameterized in terms of vertices and edges, and edges would represent binary relationships between vertices, right? And if you try to depict it pictorially, this is probably what a graph would look like. There are various kinds of graphs, and graphs are some of the most widely studied things in maths. Now I'm going to define what a cut is. Given a partition S prime, a cut is a set of edges based on that partition is a set of edges that cross the partition. For example, if we look at this example here, say the partitioning we got is S and S prime, which is S contains 1, 2 and S prime contains 3, 4. Can you guys guess what the partition cut is? Aren't you guys? Yep. Once again, so how many edges? 3. Cool. Okay, why are edges A and E not there? Precisely. So I'm going to also assume some more information. One thing that I'm going to assume is you are familiar with random variables. How many of you have actually seen random variables before? Show of hands, please. Okay. How many of you actually remember encountering this in any of the previous talks? Okay, that's pretty much all of the people. So for those who don't or haven't had much exposure to this, the random variable is just a variable that would take values randomly from a set, and often there is a probability distribution associated with it. So for any random variable we could say something like, what is the probability of that random variable assuming this particular value I, right? In our case we are going to restrict it to the case that the random variable can only take values from the set of integers, but that may not always be the case, but it's sufficient for us. Apart from that, I'm going to also assume you know what is the expectation of x. So again, how many of you are familiar with this concept? Alright, for those who don't, I'm going to briefly tell you what is required of you. Expectation of x, as I said, every random variable would have an associated probability distribution with it, and if you sampled from the probability distribution, the average value of x that you would get is represented by expectation of x. It also has an explicit expression that you can see here. So it's just the sum over all the values that the random variable can take multiplied with their respective probabilities, right? I'm going to go into a little example now. Say we have got a fair coin where the probability of obtaining a head is half, and probability of obtaining a tail is half. Now I'm going to define a random variable L, which can take the value 1 if it gets heads, and we are going to give it the value 0 if tails is what is obtained. Now the expectation of L can be given as 1 times probability L is equal to 1 and 0 times probability L is equal to 0. We are going to neglect the second term, and that would just give us the probability of heads, which is equal to half. Now is this clear? This is very important. If you have doubts here, it's a good time to clear it right now. Alright, seems like this is clear. Now the problem formulation is, if we have to state it formally, given a graph G, we need to determine the partition S prime so that the number of edges crossing the partition is maximized. Now to get a feel for this, we are going to start with an easy example. So does anybody know what kind of a graph this is? Bipartite. So it's one of those easy cases. A bipartite graph, for those who don't know, is a graph in which the set of vertices can be partitioned into two sets such that no two vertices belonging to the same set have an edge between them. So in this case the partitions are already done for us, and we can see that if you put the left vertices into one partition and the others into the other, you basically account for all the edges, which tells you that this is the most optimal solution. But how about the case where this is not a bipartite graph? How about this? Any guesses? What could be the partition for a max-cut solution? Let me, okay, do you guys agree that this is no longer so easy? Yes? Yes, no? Come on guys, you are sleeping. Okay. I'm going to go forward and say that this is one of the solutions which has got 3, 4 as part of one partition and the others as part of the other. For those who are aware of what NP hardness means, max-cut is one of those problems which happens to be NP hard. So that basically means that we have no principled way of actually solving this problem, and to actually get to the accurate solution, you basically need to run through all possible partitions, which is exponential in the number of n. Now, given the fact that this is not so easily solvable, can we do something so that we can come up with an algorithm which gives you not the most accurate result, but a result that is good enough? So the algorithm that we are going to discuss now just does that. So we start off by picking a vertex from the vertex set. We're going to toss a fair coin, and if the outcome happens to be heads, we're going to put it in one of those partitions, and if it's tails, we're going to put it in the other partition. And if we repeat this for all these vertices, then what we get is a partition, a complete partition. Does everybody understand what this algorithm is? It's pretty simple, right? Okay, so we're going to see this algorithm in action. So this is the previous example that we were discussing, and we will see, we are going to discuss, we are going to decide the partitioning of x1, x2, x3, x4, x5 in that order. So the first coin toss gives us a head, so we're going to allot it to partition 1. The second one is a tail, so we are going to give it to partition 2. The third one is again a head, so we are going to add it to partition 1. The second one is a tails. The fourth one is also tails, and the fifth one is also tails. So the partitioning that we get here is x1, x3 one side, and x2, x4, x5 is on the other partition. Now, is this the most optimal partition? Yes, no? Come on guys, you got voices. Okay. So this means that this algorithm may not always give you the most optimal partitioning, but I'm going to ask you, this is a very critical question, is this the same partitioning that we will get every time we are going to run this algorithm on this graph? No. That's apparent, right? But seems like an ad hoc algorithm. Why should it work well? And are there any guarantees as to, okay, this will at least give us some good solution? So we're going to go into that. Let's say we've given a graph with m edges, E1 to Em, and what we are going to do is, we're going to define this random variable x as we discussed. X would represent the size of the cut that we are going to compute. Why is x a random variable here? Precisely. So every time we are going to run this algorithm, the s and s prime that are returned by the algorithm could be different, and hence the randomness associated with the size of the partitions. Now what the guarantee is that the expected value of x is going to be half the number of edges in the graph. Now let's interpret it correctly. What does this say? This says that, does this say that every time you're going to run this algorithm on a given graph, it's going to give you a cut of size m by 2? Yes? No? So it's actually not. The correct interpretation of this is, if you actually ran this algorithm enough number of times and you recorded the average size of the cut would be a value that would approach m by 2 in the limit. Now this is where it would get most mathematically intensive. Feel free to stop me if you do not understand the step. Now for each edge present in the graph, we are going to define a random variable xe. Now this would take a value 1 if e happened to be in the cut, and it would take a value 0 otherwise. Now we are going to rewrite x as a sum of these xe's. Is this easy to see? Because this is the same as counting, because in the expression in the right hand side, what we are actually doing is for every edge we are adding a 1 if it's there, or 0 otherwise. So that's equivalent to counting. Now the expectation of x can again, this is the quantity that we are interested in, and that can be rewritten as the quantity in the last, which says that it's a sum of all these expectations. And why is that? It's by something known as linearity of expectations. I suppose you encountered this in Minard's talk. Yes. So what it says is, the expectation of sum of random variables is equivalent to the sum of expectation of random variables. This is only true for linear combinations. It's when you take other combinations, it may not always be true, but in our case this is good enough. Now the smallest unit of interest here is the expectation of 1 xe. So we are going to try and compute that. So I'm going to explicitly write down the expectation of xe. This is similar to what we saw for the other random variable that we defined earlier, which was L. So this is the explicit expression. We are going to neglect the second term again, because it has got a 0 multiplied with it. And I'm claiming that this is equivalent to the probability of E being present in the cut. And that is because xe is 1 if and only if E is present in the cut. So these two probabilities must always be same. Now suppose E has two endpoints, U and V. I'm going to ask you a question here. The question is, how many possible configurations there are in terms of U and V? 4. Who said 4? So let me be more explicit. One of those cases could be U belonging to S and V belonging to S prime. So yeah, so I'm going to count all cases, including the cases where E might not be present in the cut. And that gives us a total of 4 choices. Why is that? Because there are 2 choices for U and 2 choices for V. If you take them as a pair, that gives you 2 times 2, 4. It's pretty simple. And these are the cases here. Each of these cases are equally likely. I'm going to ask you, in which of these cases E is going to be present in the cut? 1 and 4. Is everybody convinced? Yes. So the probability that E is actually present in the cut is either case 1 or case 4, and there is no overlap between these two events. So we can safely say that the probability of E being present in the cut is the probability of case 1 happening plus the probability of case 2 happening. That gives you 1/4 plus 1/4, which is half. So we have been able to compute expectation of xe now. Now all that remains is to compute expectation of x, and that could be done by since xe was arbitrarily chosen, so this expectation is half for any edge, and there are m edges, so we are going to add half m times here, and that gives us a guarantee of m by 2. So that completes the proof for this. Is this clear? It's not that hard. It's you just need to know what the basics are. So this basically says that the expected value of x is going to be m by 2. Now the complexity here is again r times n. Now we need to make n choices, and every time we are going to use the random call, and that is abstracted by r. Right. Now that concludes the second 2/3 of the thing. So now here's a question. We have had we've seen some problems. We have seen some randomized algorithms for them, which seem to work reasonably well. But there is a strong assumption that we are making. Can anybody guess what this assumption is? So what connects these randomized algorithms? Yeah, so I can only hear some random something in the talk. That the claim is that here's the thing: For every time you're running this algorithm, you need to make these random choices, and it's not actually that the computer actually has a coin to toss, right? It needs to run some algorithm, and in reality the problem is that it's actually hard to produce simulate events which are truly random. In fact, as Einstein famously said, God does not play dice. So, and suppose you actually ran this for practical purposes. Say you ran this on the social network of Facebook, where there are billions of users, and you ran the max-cut algorithm on that. You basically need billions of uncorrelated random bits per second. That is a bit hard to do. So the question then we are going to ask is, suppose we were able to come up with algorithms which actually did not require these random bits, but were able to give you the same kind of guarantees as the previous algorithm, right? So now what we are going to discuss is a de-randomization of the max-cut algorithm, a version which will not actually use any of the random bits that we were talking about, right? But before that, I'm going to introduce an unrelated problem. This is totally not related, right? So we've got a tree here, and in the end of the tree there are each branch has some bananas associated with it, right? Some bananas are hanging, and the number of bananas are actually varying from place to place. Each branch has a different number of bananas associated with it, and the competitor here is a chimp, and its task is to get to the branch which has the most number of bananas for obvious reasons. Let's not go into that, but here are the rules. The rules are that you cannot, the chimp cannot backtrack. It has to go to the branch end in one shot. It cannot go visit one of the branches and then come back. But as it so happens that the chimp actually manages to get to a branch which contains at least half of the maximum number of bananas that are actually possible to obtain. I mean, you ask it to do it again, it does it again, and it does it repeatedly. So what's the trade secret? So what kind of a problem is it solving here? The kind of problem that it is solving here is that at each branch point it needs to make a decision, and the decision is of choosing whether to take the left or the right branch, and it does so by choosing the heavier branch. Now intuitively this makes sense. Why? Because if you choose the heavier branch, you are following a path which accounts for at least half of the bananas, right? Say there were X bananas available and you're choosing the heavier branch, you're guaranteed to follow a path which gets you at least X by 2 bananas. So we are going to try and get that back into our setting. So solving the max-cut problem is also like traversing through an inverted binary tree, and there's this guy sitting there trying to solve the problem, and the decision that guy has to make at each level is to say whether V belongs to S or does it belong to S prime. Now if you made enough number of choices and you made choices for all these vertices, so you are going to arrive at S and S prime. Each of these paths from root to leaf, different paths would lead to different partitions. So the analogy here is clear. The question is then, how are we supposed to make this decision, right? The decision is of choosing the heavier branch, which in our case translates to choosing the branch that will lead to a better conditional expectation. Let's elaborate. Before that, how many of you guys are familiar with conditional expectation? Very few. Alright, I'll basically go for an example now. Let's see. Okay, let's say we have a fair die, 6 choices, we are going to associate a random variable d with it. What is the probability that d is equal to I for any I, any fixed I that belongs to this set? Seems easy enough. Come on. Okay. All right. Let's go back to an even simpler example. Let's say there is this coin, and coin has two outcomes, head and tail. What is the probability that the outcome is heads, given that this is fair? What is this probability? Come on, this is one of these things we already saw in the slides. Be louder, man, come on. Half? Does anybody disagree? Seems like everybody does. Okay, I'm going to say that this is half. Similarly, for a die with 6 faces, 1, 2, 3, 4, 5, 6, the probability of obtaining any one face is equal to 1 by 6, because assuming that the die is fair, which means all of these the possibility would be chosen uniformly, so the probability of this happening is 1 by 6. But now let's say someone gave you prior knowledge that someone is saying that given the fact that D is even, so someone is saying that before you actually cast the die, that you already know, you have prior knowledge that D is going to be even. So if say let's put it as D is equal to 2, do you know what this probability is going to be? It's going to be 1 by 3. Now there is an explicit expression for computing just that. So probability of A given B is represented as probability of A intersection B by probability of B. But we are not going to go into that, but let's face it intuitively. Now if someone said that the odd numbers are eliminated, you've got only 3 possibilities, and choosing among these at random gives you a probability of 1 by 3. Similarly, if someone asked you to compute the expectation of X expectation of D, given that D is that is basically twice into probability of D given D is even, probability of 2 given D is even, plus 4 into probability of 4 times given D is even, and 6 into probability of 6 times D is even. The other possibilities are not here because of the fact that for any I, such I is odd, probability that appears given that D is even is 0. So the conditional expectation is a quantity which is this, right? So all that I want to infer out of this expression is the expectation of a particular event or random variable may change given if you got prior knowledge regarding that, and it will change in order to accommodate such possibilities. Now we are going to go back to our example here. Let's say we have already decided for vertices v1 to vt minus 1, and now we want to decide for vt, right? And in order to do that, we are going to make a decision of the kind, is alpha 1 greater than or equal to alpha 2? If so, we are going to add v to s, otherwise we are going to add v to s prime, right? Now what are these alpha 1 and alpha 2? These are basically the 2 conditional expectations that we'll need to compute, and the first one says that what is the expectation of x given that we have decided for v1 to vt minus 1, and we are assuming that we are putting vt in s. The second one says that what is the expectation of x given that we have decided for v1 to vt minus 1 and we are putting vt in s prime. understand that this decision has not already been made, but we are trying to compute the expected values of the size of the cut if either of these decisions were made. Whichever gives you the better conditional expectation will basically take the path through that. So if alpha 1, meaning that assuming that Vt is put in S gives you a better conditional expectation, we are going to choose put V in S instead of S prime. And for the other case, it's exactly the opposite. Now this algorithm, you can do this for all this starting from V1 to Vn, whatever number of vertices, and if you did this again and again and you arrived at a partition, the algorithm output has exactly the same guarantees as they had in the randomized case, which is saying that it would basically give you a cut which is of size in expectation m by 2. And the proof is simple, but we are not going to go through it. It's based on induction on T for those who are interested. Now there is a catch here. So we had a randomized algorithm which had some guarantees. Now we managed to remove the randomness and we are still able to get the same kind of guarantees that we had. Then the question here is, are we just being smarter or is there a trade-off, right? And there is actually a trade-off. Can anybody guess what the trade-off is? So what's different from this algorithm and the previous one? It's in the way we make the decision. Does everybody agree? Because the procedure that we're following is exactly the same. We're deciding partitions for each vertices one by one. And while the first algorithm actually used random bits, here we are having to compute these conditional expectations. And doing so may not always be efficient. It depends for different applications. But in the case that we have an efficient way of computing this expectation, what we actually have is an algorithm that gives us the same kind of guarantees as the randomized algorithm. And we are not having to use any randomness at all. So to conclude, we saw some problems, some hard problems, and we saw that there are polynomial time randomized algorithms for those, which gives us reasonably good guarantees. We had some, we also saw the need for de-randomization of those algorithms, and we saw why de-randomization was necessary. So there are also plenty of open questions here if someone wants to pursue this further. For example, there are a lot of randomized algorithms for which de-randomized versions have not been found. For example, the AKS algorithm that we mentioned earlier is one of those landmark breakthroughs in the 21st century that actually gave us the first algorithm which was deterministic and polynomial in log n and was able to do primality testing accurately. Plenty of other problems are there that do not have de-randomized versions, and if someone is actually able to make a de-randomized version for them, that will be considered a significant breakthrough. Apart from that, there are also plenty of hard problems for which no randomized algorithms exist, and in fact such questions are unanswered, such as what makes these algorithms hard to randomize or de-randomize. So there are plenty of questions here if someone wishes to pursue randomized algorithm as workplace, as a field of work, and that should basically conclude my talk. If you've got questions now would be the time to ask.
Sir, can randomized algorithms be used in real-time situation for real-time systems?
They are pretty much used in real-time systems. For example, we saw two follow-ups to the primality testing algorithm. One was the Miller-Rabin test and the other was the AKS algorithm. In practice, it's the Miller-Rabin test that is used because it's a lot more elegant and it's much more faster. So as it so happens, for most of these algorithms that also have a de-randomized version, the randomized version is much more simple and elegant to implement than the de-randomized counterparts. So they're very prevalent in places that you look at. There are other applications that we did not talk about. For example, if you needed to match two matrices, right? The randomized algorithm is one of the best techniques out there. So there are other places where the randomized algorithm beats every other algorithm hands down. Any other question? Okay, then I'm going to ask you a question. All right. So the kind of algorithms that we saw had fixed running times and probabilistic guarantees on the optimality on the accuracy that we got. There is this other class of algorithms that has fixed guarantees on optimality. Would probably always it will always give you the correct result, but there are probabilistic guarantees on how long it would run. Have we come across any such algorithm? I'm pretty sure you have. Okay. I'm going to ask you, has anyone heard of an algorithm called quicksort? All right. Does anybody know what the worst case running time is? N squared, and that happens when it's sorted in reverse order. But and what people usually do is, for those who know, they usually, instead of fixing, determining the pivot deterministically, they determine the pivot randomly, and that algorithm would always return you the exactly sorted array, but the number of comparisons it would require to get to that sorted array is something that is random, and there are only probabilistic guarantees on that. Here is an interesting fact. The fact is that any such, most problems belonging to that class of algorithms which has got fixed fixed guarantees on accuracy and probabilistic running times can be converted into our class of algorithms that we discussed, which has got fixed running time kind of thing and probabilistic guarantees on the optimality, but not the other way around. So that is probably all that I had to say. Thanks for staying.
So next is